Hello everyone. Today we are gonna cover unit 4 of the syllabus for data structures, and the name of the unit is trees. Okay, so going ahead with the introduction, a tree is a hierarchical data structure which stores the data which is in the form of hierarchical style. Okay, so what do you mean by hierarchical data? So we can say, for example, we can take a family tree. We have our ancestors, then the ancestors, for example, we have a great grandfather, then we have a grandfather, then father, then next uncle. So there's a family tree which is formed. To store such hierarchical data, we can use trees. Okay, now we can take another example of the college management data. For example, we have at the higher position, we have principals, sir, then we have the deans, then we have the HODs, then we have the lecturers. So this forms a hierarchy, and to store this hierarchical data, we can use trees. Okay, now tree is one of the most powerful and an advanced data structure. Okay, the next point what we have to make a note is, till now we have studied linear data structure. Now what we are going to discuss, the trees, is a non-linear data structure. Okay, next here the tree is represented with the nodes connected by the edges. So in the further slides we will look at how the tree looks with nodes and edges. Okay, moving ahead to the next slide. This slide mainly concentrates on binary tree. Okay, so as the name suggests, binary tree, this particular tree has only two children. Okay, so binary means two, so it has only two children, the left and the right child. Okay, so binary tree is a special data structure used for data storage purposes. Okay, now how do we define a binary tree? A binary tree is the one whose elements have at most two children. Okay, there cannot be more than two children. Okay, so what we see, since each element in a binary tree can have only two children, we typically call them as the left and the right child. Okay, next, a binary tree has a special condition that each node can have a maximum of two children. So there is another definition of a binary tree in another form. It says a binary tree has a special condition. So see, we can segregate a tree and a binary tree. How are we going to segregate a binary tree? Is by making or by understanding this special condition, that is, each node in the binary tree can have a maximum of two children only. Okay, the next point is, a binary tree has benefits of both an ordered array and the linked list. Okay, next, now what we say an ordered array and linked list, we have studied linked lists in which we have searching operation, right? So here binary tree has both the array advantages of an array, it also has advantages of linked list. Then so it's a combination. There are features from or arrays as well as linked list which can be understood or which can be seen in a binary tree as well. For example, there is insertion operation, deletion operation, there is search, okay, that goes on. Okay, so this is nothing but the definition of the binary tree. The most apt and the simple definition what we can say is, a binary tree has a special condition that each node can have maximum of two children. Okay, next, how does a binary tree look like? So this is the example. There is the main node which is called as the root node. This main node has only two children, which is B and C. So we see that there's no one more child. Okay, there's no, after B, C, there's no D. There's gonna only be B and C. B further has D and E. There's no again one more split up. B also can have at most of two children. At any point of time, the number of child nodes will be 2, at most 2, that is maximum of 2. Here you see there's J, that's okay if there is no node. Okay, but it cannot have more than 2 nodes. Okay, so here let us see. Now H and I are called as the child node, and the parent of H and I is D, which is called as the parent node. This itself forms the structure called as the subtree. Okay, next, if next definition we can take up as F and G. Okay, so now here F and G are child nodes of the parent node C. F and G are related as siblings. Okay, and if you observe, F doesn't have further any child node, so this is the last node of this particular parent node, so hence this is called as a leaf node. Okay, next point, we can see there are different levels. So at level 0 we have A, level 1, level 2, level 3, we have different hierarchical levels. Okay, so this is all in all an example of how a binary tree looks like and different definitions. Okay, so here I have stated few of the definitions. Okay, so what is path? It refers to the sequence of nodes along the edges of a tree. Okay, then we have a root node. What is it? The node at the top of the tree is called a root node. Okay, so the first node or the main node of a tree is called the root node. Okay, so there is only one root node. Remember, there is only one root per tree and one path from the root node to any node. There cannot be multiple root nodes, only one main node that can be called as the root node. Okay, next definition, as discussed, any node except the root node has one edge upward to a node called as parent. So you can see here this node is called as the parent node. So what we say, any node except the root node has one edge upward to a node called as parent node. Okay, next, child. The node below a given node connected by its edges downward is called the child node. So we see here this node is connected downwards with an edge, hence this node is called as the child node. Next is the leaf node. The node which does not have any child node is called as the leaf node. So if you observe here, this F doesn't further have any child node, hence this is called as a leaf node. Next is the definition of a subtree. Okay, what is a subtree? So the subtree represents the descendants of a node. So here this is nothing but a subtree. So you see this is the descendant. Okay, and this itself is one more small tree. Don't you think so? There's node and there are two children. So this in turn is called as a subtree. Okay, visiting. What do you mean by visiting is refers to checking the value of the node when control is on the node. Next is traversing. Traversing means passing through nodes in a specific order. Okay, here further we are going to study what is traversing. Okay, so traversing means passing through each node in a specific order, traversing the tree. Okay, so I can traverse the tree from root node to the left node. Okay, I can traverse the tree from the root node to the right node and further. So there are different type of traversing what we will be studying. Okay, next, levels. So I have given an example of levels as well. Level of a node represents the generations of a node. Remember, I gave you an example of a family tree, that is your grandfather. Yes, that will be a great grandfather. Sorry, great grandfather will be at level 0, grandfather will be at level 1. So then is your father, correct? So there are different levels of generation that can be represented. Or for example, say principal at level 0, then comes the deans at level 1. So this hierarchical tree can be denoted by different levels. So what we say, the definition is, level of node represents the generation of a node. If the root node is at level 0, then its next node is at level 1. Remember, its grandchild is at level 2 and so on. This is how the hierarchical data is formed. Next definition, keys. Key represents a value of a node based on which a search operation is to be carried out for a node. Okay, simple. Key is nothing but it represents the value, that is the data value of the node based on which we can carry out the further search operation. Okay, next we discussed what is a tree, then a binary tree, then different definitions. Okay, now let us see why trees. Okay, so basically, unlike array and linked list, which are linear data structure, tree here is a hierarchical data structure. So here we can store the data in the hierarchical fashion. So we need trees. Okay, for example, let us take the file system on a computer. Have we seen we have this format, that is we have root, then we have home, yeah, then we have the file. Okay, how this data is saved onto the computer? It is nothing but it is saved in the form of trees. Okay, because if you observe here, this is also forms a hierarchy. You have root folder, then you have your home folder, and in that there is course folder, and then there are files CS101, CS112, CS113. So this hierarchical data can be stored in the data structure called as trees. Okay, next point. Okay, if we organize keys in the form of tree, okay, we can search for the given key in moderate time. In moderate time, we mean that quicker than the linked list and slower than the arrays. So if we know that arrays, there is indexing 0, 1, 2, 3, right? So if we have to search in arrays, we search on the index of the key element. When we find it, when the match is found, we print it, right? Here, in case of searching the data, okay, there is a moderate time what is involved. Okay, it is quicker than the linked list and slower than the arrays. So this is one of the reason. Here we can see an advantage as well as a disadvantage. So the main point is use the appropriate data structure when you are implementing a problem statement. Okay, so if you need time to be you need search time to be quicker than the linked list, you're free to use trees for that data, right? So this has to be clear in mind. Appropriate data structure should be used while implementing a particular problem statement according to what is our requirement. Okay, next point, we can insert delete keys in a moderate time. So we can insert the data, we can delete the data in certain time. So here in case of trees, it is quicker than the arrays and slower than the unordered linked list. Okay, next important point, like linked list and unlike arrays, pointer implementation of trees doesn't have an upper limit on the number of nodes, as nodes are linked using pointers. Okay, here what this point states is, we all have studied linked list in the previous lectures, correct? So we have seen that we are using pointers. Okay, so we are using pointers to point to the next node. So what we say, or what is said, that pointer implementation of trees don't have any upper limit on the number of nodes. We don't have any upper limit on the number of the nodes. It can be 1, 2, 3, 4, 5, 6, 7, 8. So it goes on the linked list, right? It depends upon what is the requirement. So there is no upper limit on the number of nodes, in just like in case of your linked list. This also applies to the trees. So whenever we have trees, like if we are implementing a binary tree, we don't say we are gonna have only two, say we are gonna only have 3 levels or 4 levels. You can go on adding your tree as per the requirement. Okay, next, what are the applications? Okay, so here let us concentrate on few of the main applications, which says store the hierarchical data. Yes, we now have understood it is important to store the hierarchical data, like folder structure, organization structure, XML, HTML data. Yeah, XML and HTML data can also be used, can be saved using the tree data structure. Next important point, Binary search tree is a tree that allows fast search, okay, quick search. Have we seen like the folder organization, right? We get a quick search, so it is like binary search tree BST is a tree that allows fast search, insert, delete on the sorted data. Okay, next important application is syntax tree, which is used in the compilers. One important application in terms of electronics engineers, yes, this is the one, that is spanning trees. We will be studying the spanning trees and the shortest path trees that will be used in routers and bridges. Okay, so these also are the form of the trees. Okay, so this we will be studying in computer networks. Okay, next, binary search tree. Okay, now we studied general binary tree. Now next we are going to study BST, binary search tree. Okay, in this case there is a particular format in which you are going to form a tree. Okay, so make a note of how a BST tree is formed. Okay, binary search tree exhibits a special behavior. Okay, a node's left child, remember, a node's left child. Okay, this is a node. A node's left child will have a value less than its parent node, and the node's right child must have a value greater than its parent node. Okay, now here if you observe this node, we call it as a root node. Okay, the left child 14 is less than 27, hence it will be the left child. Next data is 35 is greater than 27, hence it is going to be the right child. Okay, let us see further. Okay, so this is one subtree, right? 14, 10, 19 form a subtree. Here 14 is the node. There will be only one root node. So 27, what we call this node, this node will be the root node. This further will be the parent node. This will be the child node. Okay, so now if I have to make a tree, BST tree, the data on the left side should be less than the parent node. See here, so 10 is less than 14. Next, the data onto the right node should be greater than the parent node, so 19 is greater than 14. Similarly here, 31, the left child 31 is less than 35. 42, the right child is greater than 35. This is how we form a binary search tree. Okay, so this is very important. This is the way we have to organize the data in the BST for further simplifying our search process. Okay, next there are few operations, okay, that can be performed onto the BSTs. Okay, the first one, what we say is insert. That is nothing but inserting an element into a tree, and then we start creating a tree. If we have to insert the first element, we start creating tree, right? So there is insert operation. Next is search. If we have to search an element in a tree, we traverse the tree and then we searched an element. So this is one more operation. Next, traversal. So there are three different types of traversal called as pre-order traversal, in-order traversal, and post-order traversal. We will look into this operations at a later stage. Okay, in detail. As of now, we know what is insert and what is search. Let us look into details of insert and search. Okay, before going to them, let me tell you all how we can represent a tree node in case of the programming, or how we can put it in form of a program. Okay, so what we say here is struct node. Okay, now we know node, right? We are going to implement a binary tree. There should be left child and right child, correct? We can now recall the linked list. In linked list, what we have the data part, then the address which connects to the next node, right? So there are two parts. One is the data and then the address, but that is the pointer address, right? Next, here what important point is, we have a left child and a right child. Okay, so we need a pointer to the left child as well as we need a pointer to the right child. Okay, so we have data, which can be of any data type, then struct, the self-referencing to the structure node with the pointer left child and the pointer right child. So this completely is the structure or the tree node implementation. Okay, next let us look into how an insert operation can be performed. Okay, so now the very first insertion what we do, it does create a tree. Okay, because there's no data, the first insert will start creating the tree. Next, whenever an element is to be inserted, remember, whenever an element is to be inserted, we first locate the proper location. That is, we need to know, if we have to insert any data, we need to know whether we are going to insert the data at the left or at the right. We need to figure out what location is proper location so as to insert this data. Okay, to start, how we are going to do is, we are going to start searching the tree right from the root node. Okay, so we start searching right from the root node. Then if the data is less than the key value, what we do, we search for the empty location in the left subtree. Correct. Now I have already explained how a BST is formed. That is, we have a root node. Then if the the left child will always have the value less than the parent node, the right child will have a value always greater than the parent node. Similarly, if we have to insert, we have to find the appropriate location. To do that, we start searching right from the start, that is right from the root node, and then we figure out the proper location. So if we have to insert a number which is less than the parent node, we start searching in the left subtree where there is an empty location and then make an insert. Okay. Otherwise, we search for the empty location in the right tree. If the value is greater than the parent node, what we do is we search for an empty location in the right subtree and insert the data. Okay. Next operation. Okay, this is what we have done. This is the insert operation. The next what we have to discuss is the search operation. Simple, correct? The same concept applies. What we are going to do is start searching right from the root node. Okay. If the data, if what we want to search, okay, is less than the key value, search for the element in the left subtree. Understanding now why this BST is formed in this fashion, that is, the left tree is having the less value than the parent node, the right tree is having the value greater than the parent node. Hence there is an advantage of tree, that is, the search is much quicker, right? Okay, so we continue. So if the data is less than the key value, search the element in the left subtree, else search the element in the right subtree, and keep repeating the steps until you encounter the value what you are searching for. Once you encounter the value what you are searching for, we print that particular data.